Hello students, next let us start with the properties of discrete time Fourier transform. First is the linearity property. Linearity property says that if we are having two signals or two sequences x1 of n and x2 of n, then we can add both of them by after multiplying with a constant. Then in the Fourier transform also their individual Fourier transforms will be multiplied by the same number. I should not have written capital A here. It should be written small a itself because that is the number that is here. So small a multiplied with x1 of omega and small b multiplied with x2 of omega. This is what the Fourier transform will be. Okay, so let us prove this. We know that the Fourier transform of the combination will be given by summation n is equal to minus infinity to infinity a x1 of n plus b x2 of n multiplied with e raised to power minus j omega n. Now we can split this into two components. One is for this one and another one is for this one. So we can write it that this is equal to summation n is equal to minus infinity to infinity a x1 of n e raised to power minus j omega n plus summation n is equal to minus infinity to infinity a x1 of n plus b x2 of n. Sorry, I have to only write the second portion, which is b x2 of n e raised to power minus j omega n. If I take a, which is a constant here, if I take that a outside this particular summation, I will get basically summation of x1 of n e raised to power minus j omega, which is basically a multiplied with whatever is inside the summation. That is the equation of the Fourier transform of x1 of n, which is x1 of omega, plus here also b is common. Whatever is inside the bracket, whatever is inside the summation is basically the Fourier transform of x2 of n, which is x2 of omega. Hence proved. The next is the time shifting property. The time shifting property basically states that if we are having a function x of n whose discrete time Fourier transform we already know, then we can find out the discrete time function, discrete time Fourier transform of the shifted signal by just multiplying with the original Fourier transform a factor which is e raised to power minus j omega m, where this m basically comes from the shifted value minus m. Let us prove this. Let us first put it in the equation. Therefore the Fourier transform of x of n minus m, the Fourier transform is given by summation n is equal to minus infinity to infinity. Instead of x of n, I will write x of n minus m e raised to power minus j omega n. Now we can put a new value for n minus m. Let me put a variable p. So based on that, now the summation will change from n to p. Similarly, inside the equation also it will change. Therefore, this is going to be equal to summation n is equal to, not n, p. P is equal to, now what should be the value of p? According to this equation, n should be equal to p plus m. Or if I are going to look here, then for n is equal to minus infinity p is going to be minus infinity. For n is equal to plus infinity, again p is going to be plus infinity. So actually the limit will not change, it will be from minus infinity to infinity. And then instead of x of n, I will write x of p e raised to power minus j omega. Instead of n, I will write p plus m, from which I can take this m component outside and I will write it as, this is equal to summation p is equal to minus infinity to infinity. Okay, write it properly. Minus infinity to infinity x of p e raised to power minus j omega p, and the other e raised to power minus j omega m I will take outside because it is not dependent on p, and only this much factor needs to be inside the bracket. Therefore from here I can say, therefore this is equal to e raised to power minus j omega m, and this whole thing can be written as capital X of omega. Hence we have proved this, so I will have to write, therefore the Fourier transform of x n minus m is going to be discrete time Fourier transform. Discrete time Fourier transform of this is going to be e raised to power minus j omega m x of omega. Now if this is going to be plus m, so I can write it as either plus or minus m. Generally if it is plus m, then here it will be plus. Okay. Next is the frequency shifting property, which states that if you are having a function x of n whose DFT you have already calculated, then if you want to shift the frequency, all you have to do is multiply with that function e raised to power j omega naught n, where omega naught is the frequency value with which you want to shift. So the Fourier transform of x of n e raised to power j omega naught n will be given by the equation summation n is equal to minus infinity to infinity x of n e raised to power j omega naught n into e raised to power minus j omega n. Here we can join these two exponential portions together, and we can write n is equal to minus infinity to infinity x of n e raised to power, I will write minus j as such, okay, so that omega minus omega naught is what is coming, and then n is again common to it. So this is what, this is basically the Fourier transform of x of n, but instead of omega we are having instead of omega we are having omega minus omega naught, so I can write it as x of omega minus omega naught. Okay, so it's a quite simple property, hence proved. Next, let us look at the fourth property. The time reversal property says that if you are having a discrete time Fourier transform of x of n as x of omega, then the discrete time Fourier transform of x of minus n will basically give x of minus omega. That means whatever is x of omega, instead of omega you put minus omega. We know that the Fourier transform of x of minus n will be given by summation. Instead of x of n we will write x of minus n. Now let us put n is equal to minus n. So if I am going to put that, then this equation summation will be from actually n is equal to plus infinity to minus infinity, and x of minus n will become x of n, and you will have e raised to power minus, instead of minus it will become plus, because the n is going to be minus here, so it is going to be plus j omega naught n. I will not write omega naught, I will write omega, sorry. So it is omega n. Okay, next put omega is equal to minus omega. Then what will happen? Summation Anyway, it is from infinity to minus infinity. I can write it reverse also. That means I can write it from minus infinity to infinity. It does not matter, because you either count from minus infinity to infinity, or you go from infinity to minus infinity. It is one and the same thing. So I can change this in this particular fashion, and then the remaining x of n will remain as such x of n, and e raised to power, instead of omega I will write minus omega n. Okay, now this is what? This is the equation of the Fourier transform of x of n. Therefore I will write this as x of omega, where omega has been replaced as minus omega, hence proved. Let me do this small correction here. This if I write a minus here, then I will have to write a minus omega here, sorry. So that minus omega will come here. Okay. The differentiation and frequency domain property states that if you are having a function x of n whose x of omega you have found out, then multiplying the time n with x of n, if you want to find out the Fourier transform of that, it is as good as taking the original x of omega that you found out and then differentiating it with respect to omega and multiplying it with j. If it is with n square, you will have to multiply it with j square and double differentiate with respect to omega. Let us prove this. We will start in the reverse order. That means, suppose if we already know x of omega, what is the differentiation of x of omega with respect to omega? For finding that, I will have to differentiate with respect to omega the equation of x of omega, which is summation n is equal to minus infinity to infinity x of n e raised to power minus j omega n. Now since there is no omega either here neither here, only omega is here, so what will happen is that the differentiation will act only on that particular function. So I will rewrite this as summation n is equal to minus infinity to infinity x of n as such is there, and we are trying to take the differentiation with respect to omega of the function e raised to power minus j omega n, which you can see is going to be minus j n into e raised to power minus j omega n. So I will write this as, this is equivalent to summation n is equal to minus infinity to infinity x of n into minus jn into e raised to power minus j omega n, which minus j I can take outside, so I will have minus j outside, and the remaining portion I will write within brackets summation n is equal to minus infinity to infinity and x of n into n, that n I will write in the front, into e raised to power minus j omega n. So what is this? This is basically the Fourier transform of the function n x of n, correct? Therefore I will write this as the Fourier transform of, so this is equal to minus j into the Fourier transform of n x of n. Where did we start from? We started from here. So what is therefore Fourier transform of n x of n? So minus j will go to the other side, that means minus j will come to the left hand side of this, which is basically, so this is equal to minus j will, when it comes to the other side, becomes plus j, okay, because minus j the other side becomes 1 divided by minus j, which is equal to j. Okay, it's not addition going into subtraction, it is addition going to the other side. So here it is minus j and here it is d by d omega of x of omega. So if I take this minus j the other side, it will come as 1 by minus j, which is actually j. So that is what I have to write. So I will write it more neatly. Therefore this is going to be j into d by d omega of x of omega, hence proved. The time convolution property basically states that if you are having function x1 of n whose Fourier transform is x1 of omega, and another function x2 of n whose discrete time Fourier transform is x2 of omega, then convolution of these two functions will give us new function, and that new function can be the Fourier transform of that new function can be found out by basically multiplying the Fourier transform of the two functions. So basically convolution in one domain will lead to multiplication in the other domain. This always we have seen these kind of properties in other transforms also. Let us prove this. We know that the Fourier transform is basically given by n is equal to minus infinity to infinity the function x1 of n convolution with x2 of n e raised to power minus j omega naught n. But what is the equation of convolution? The equation of convolution, I will use a different color for that. The equation of convolution can be given by, let me use this color, summation. Let me use another variable which is k. So k is equal to minus infinity to infinity x1 of k into x2 of n minus k. This is the equation of convolution. Okay, the remaining portion we will write as such, e raised to power minus j omega naught n. Now we can interchange the order of summation. Interchanging the order of summation, we get, so what I'm going to do is I will take the k portions out. So let me use the same color that I have used above. So k is equal to minus infinity to infinity x1 of k. So that has come outside. The remaining portion I will keep it inside. So summation n is equal to minus infinity to infinity, and then the remaining function x2 of n minus k e raised to power minus j omega naught n. Sorry, I have to use the color that I have used. So e raised to power minus j omega naught n. Okay, now we will say put n minus k as a new variable p. Then in that case what we will have is, let us rewrite the equation. So summation k is equal to minus infinity to infinity x1 of k, and the summation n is equal to minus infinity to infinity x2 of p. So if I am going to put p, obviously the limits will also change. So here also I will have to make it p. Okay, the limits are going to change, and e raised to power minus j omega naught. Now instead of n I will write n is equal to p plus k. So that p plus k I will write here. Now here what I will do is I will split these two into two parts, e raised to power minus j omega naught p and e raised to power minus j omega naught k. This e raised to power minus j omega naught p I will use here itself, whereas e raised to power minus j omega naught k I will take it to this side. So if I rewrite that, and now I will use only black color because now I can write it, summation k is equal to minus infinity to infinity x1 of k into, from here, e raised to power minus j omega naught k, and then summation p is equal to minus infinity to infinity x2 of p e raised to power minus j omega naught p. What are these? Basically, if you would see, this is the Fourier transform of x1 of k, whereas this is the Fourier transform of x2 of p. That means only the variable has changed. So this is basically the Fourier transform of x1. So it will be x1 of omega multiplied with, because now it is straight away multiplication here, multiplied with the Fourier transform of x2 of p or x2 of n, which is x2, capital X2 of omega. So hence proved. Next property. Next is the frequency convolution property, which states that if you are having a function x1 of n whose Fourier transform is given by x1 of omega, and another function whose Fourier transform you know, then the Fourier transform of the multiplication of both the functions will be the convolution of the DFT, individual DFT. Let us prove this. We know that the Fourier transform of any function is basically summation n is from minus infinity to infinity, then the function, which in our case is the multiplication of x1 of n and x2 of n, multiplied with e raised to power minus j omega n. Now here I am going to substitute, instead of x1 of n, I am going to substitute the Fourier inverse. That means I am going to put x1 of n as the Fourier inverse of x1 of omega. Okay, but instead of omega I am just going to write theta because I want a different variable. Okay, so x1 of n is basically, we know that x1 of n and x2 of n are interchangeable. That means the DFT of x1 of n is x1 of omega, and similarly from x1 of omega I can find back x1 of n. So that is what the Fourier inverse here means by. Okay, so the Fourier inverse, and we have already seen the formula of the Fourier inverse, the inverse DFT. Okay, so that into x2 of n e raised to power minus j omega n. Now in a fresh page, let me write the equation of the Fourier inverse of x1 of theta. So now the equation is summation n is equal to minus infinity to infinity. Now what is the equation of Fourier inverse? The equation of Fourier inverse, let me use a different color here. So the equation is going to be 1 by 2 pi, is going to be 1 by 2 pi integration from minus pi to plus pi, because it is periodic. Okay, and then x1 of theta e raised to power j omega, instead of omega it is theta n. D omega can be written as d theta. Okay, and then the remaining portion x2 of n is there, and e raised to power minus j omega n x2 of n. Okay, now here I will interchange the order of summation and integration. So first I will take the integration outside. So I will write this is equal to, let me use the color that I had used. So 1 by 2 pi integral minus pi to plus pi x1 of theta. Okay, and then there is no other term, only of theta, so the remaining portion I will put it inside the bracket, and then we are having summation n is equal to minus infinity to infinity, and then e raised to power j theta n and e raised to power minus j omega n x2n. Okay, so these are all with respect to n, and then we are having the last, the d theta portion, which I can write it here, d theta. Okay. Now these two can be joined together. So I will first write x2 of n here, and then e raised to power minus j omega minus theta n together in the bracket, and then we are having the d theta portion. Okay. Now what is this? This is the Fourier transform of x2 of n with respect to omega, with respect to omega minus theta. Okay. So we will replace that. So again I will write the equation as this is equal to 1 by 2 pi integral minus pi to plus pi x1 of theta, and whatever is inside the bracket, it is the Fourier transform of x2 of n, which is x2 of omega minus theta, okay, and then the remaining d theta. Now what is this? This is basically the equation of the convolution between x1 and x2, isn't it? So therefore I will write this is equal to the convolution between x1 of omega with x2 of omega. This is the equation of convolution. Okay, hence proved. Next property is the modulation property, which states that if x of n is having a Fourier transform of x of omega, as it is shown here, then multiplying x of n with a cosine function, which we generally do in case of modulation. So if you multiply x of n with a cosine function, then you will have multiple replicas of x of n, one at plus omega and another at minus omega. So this will be at plus omega, this will be at minus omega naught. Okay, so this will be at plus omega naught and this will be at minus omega naught. This is something that we have already seen many times. Let us prove this. The Fourier transform of x of n cos omega naught, first thing that we can do that is we can write x of n in terms of Euler's relation. So I will write x of n multiplied with, we know the formula, e raised to power j omega naught n plus e raised to power minus j omega naught n divided by 2. That is the Euler's relation for cos omega naught n. Okay, therefore this equation, the Fourier transform equation, is going to be summation n is equal to minus infinity to infinity. I will write two parts of the equation. The first part will be this 1 by 2 x of n e raised to power j omega naught n into e raised to power minus j omega n. This is the first part of this much portion, and next part is of this portion with x of n by 2. So that I will write it as plus summation n is equal to minus infinity to infinity 1 by 2 x of n e raised to power minus j omega naught n into e raised to power minus j omega n. Okay, which I can write it as 1 by 2 I can take commonly outside, and the remaining is summation n is equal to minus infinity to infinity x of n and then e raised to power minus j omega plus omega, not plus, it will be minus omega naught n, okay, minus omega naught n, plus the second summation will be summation n is equal to minus infinity to infinity 1 by 2 I have taken outside x of n e raised to power minus j commonly taken outside, so omega plus omega naught n, correct, which is what? This is the Fourier transform of x of n, but instead of omega it is omega minus omega naught. This is also Fourier transform of x of n, but here instead of omega it is omega plus omega naught. So I can write this as, so half of x of omega minus omega naught plus x of omega plus omega naught, hence proved. Next is the Parseval's theorem, which is basically stating that if you are having a x of n whose x of omega you have already calculated, then you can find out x of n energy, that means the energy of x of n, using this formula, because it's a discrete sequence. At the same time, if you know x of omega, you can calculate the energy directly from x of omega using this particular equation, which is the energy inside the spectrum, inside the frequency spectrum. What basically the Parseval's theorem states is that whatever is the energy you calculate in the time domain, the same energy you will get in the frequency domain also. That is basically what this is trying to say. So let us prove this. We know that the energy of a signal, which is given by summation n is equal to minus infinity to infinity sum of x of n magnitude square, which x of n magnitude square can be actually written as summation n is equal to minus infinity to infinity. The xn magnitude square can also be written as x of n multiplied with the conjugate value of x of n. The conjugate value of x of n. Now, if I want to find out what is x of n with respect to its Fourier inverse, that means I can write that energy is equal to summation n is equal to minus infinity to infinity. Now, the conjugate value of x of n I will write as such. Then the second portion can be written as a Fourier inverse. What is a Fourier inverse? 1 by 2 pi from minus pi to plus pi x of omega d omega e raised to power j omega n d omega. This is what is the Fourier inverse. That means this is what is the Fourier transform. So if I know what is the Fourier transform of x of n, which is x of omega, I can find out x of n by using this formula, but there is a conjugate here, so I have to put a conjugate for the whole thing. So writing that in this part of the equation, which I will now write it as with the help of a different color. So 1 by 2 pi integral minus pi to plus pi x of omega e raised to power j omega n d omega conjugate, wherein if I try to bring the conjugate inside, if I try to bring the conjugate inside, I will get n is equal to minus infinity to infinity. X of n is as such there. 1 by 2 pi I can write it outside as 1 by 2 pi. Let me use a different color, because so is equal to 1 by 2 pi I will take outside. And then the integral minus pi to plus pi x of omega, I will take the conjugate inside, so x of omega conjugate e raised to power minus j omega n, because that is the conjugate of this one. That is the conjugate of e raised to power j omega n, and then d omega. D omega, again I will have to use the different color, so let me use d omega. Now I am going to interchange the order of summation and integration. So what I will basically do here is I will take the d omega terms outside. So this x of omega integral from minus pi to plus pi, I will take it here, and within summation I will have x of n e raised to power minus j omega n. So let me do that in a fresh page. So changing the order of integration, I have brought the integration out, and then the remaining portion within the brackets I will put it inside. Let me use the different color. So that is summation n is equal to minus infinity to infinity x of n e raised to power minus j omega n. And then the remaining portion is basically d omega, which is outside. Okay. Now what is within this brackets? Within this bracket we are having the Fourier transform of x of n, which is x of omega itself. So now I will write that this is 1 by 2 pi integral minus pi to plus pi x conjugate of omega, and within this bracket what we are having is x of omega, that is a Fourier transform of x of n, and then d omega. Now what is the multiplication of the conjugate with itself? It is magnitude square. So I will write this as 1 by 2 integral minus pi to plus pi magnitude of x of omega square d omega, which is basically the right hand side of our equation from where we started. So this is also proved. Now based on this, let us try to get some solved examples. Find the DTFT of the following sequences. The first one is delta n plus 3 minus delta n minus 3. So basically for solving, I will use the concept. We know that delta n, if you would try to take the Fourier DTFT, its value comes as 1. Using formula, so using which property? Time shifting property. Using time shifting property. And what is the time shifting property? Says that we have just now studied. Time shifting property basically says that if you are having a function x of n minus n naught, its Fourier transform or DTFT is going to be x of n, capital X of omega e raised to power minus j omega n naught. So using that property, I will write that the DTFT of n plus 3 is going to be 1 into e raised to power minus, since this is plus, this should be plus, so j omega 3. And the delta n minus 3 will give a DTFT of e raised to power minus j omega 3. Therefore, I can write delta n plus 3 minus delta n minus 3, the Fourier transform of that, which I will now write it as the Fourier transform of that, is going to be equal to e raised to power j omega 3 minus e raised to power minus j omega 3, with which if I am going to multiply and divide by 2j, if I am going to multiply and divide by 2j, then what is inside the bracket? Inside the bracket is sine, isn't it? Because based on Euler's relation, this will be, within the bracket will be sine 3 omega into 2j. So 2j I will write in the front. So this is equal to 2j sine 3 omega. So that is the Fourier transform of this particular function. Next is the signal x of n is equal to u of n plus 3 minus u of n minus 3. Okay, u of n plus 3, u of n minus 3, minus u of n minus 3. So what is the Fourier transform of that? We know that the Fourier transform of u of n, that is the DTFT of u of n, is basically given by 1 divided by 1 minus e raised to power minus j omega. Okay, let me write this properly. Therefore using which property? Time shift property. Time shifting property. What is the time shifting property? This is the time shifting property which we have just now seen. Therefore, based on that, I can write that the Fourier transform of u of n plus 3, so let me write that both of them together. So the Fourier transform of u of n plus 3 minus u of n minus 3 can be given as, so if I am going to use this same principle, I will get e raised to power minus j, since it is plus 3, so here also I will have to write plus j omega n naught, which is 3, divided by 1 minus e raised to power minus j omega. Similarly, for the second case, it will be e raised to power minus j omega 3 divided by 1 minus e raised to power minus j omega. Now here I can write this thing totally as e raised to power j 3 omega minus e raised to power minus j 3 omega divided by 1 minus e raised to power minus j omega. Okay, and here I can multiply and divide it with 2j, so I will get 2j e raised to power j 3 omega minus e raised to power minus j 3 omega, and this divided by 2j. Okay, why I am doing that? Because I want to convert it into sign. And here, if you would remember, we had already done something like 1 minus e raised to power minus j theta. If I take theta by 2 outside, so I will get e raised to power minus j theta by 2 outside, because of which this will become e raised to power j theta by 2 minus e raised to power minus j theta by 2. Isn't it? So that same principle I will use here. This I will write it as e raised to power minus j omega by 2 into e raised to power minus j omega by 2 minus e raised to power minus j omega by 2. Okay. Now here is something very interesting. Now here this numerator will basically become 2j into sine of 3 omega. Using what? Using the Euler's relation. And in the denominator, now I will multiply it with, suppose, 2j. So what I will do is I will divide this with 2j and multiply it with 2j. So this will also become a sine. So it will become sine omega by 2. And here the 2j e raised to power term will be coming. So I will write 2j here. And e raised to power j omega by 2 term, if I take it to the numerator, it will become e raised to power j omega by 2. Okay. Now from that we can conclude that the Fourier transform of u of n plus 3 minus u of n minus 3 is going to be equal to 2j gets cancelled off, sine of 3 omega divided by sine of omega by 2 into e raised to power j omega by 2. Now this problem has a small significance because, see, if I am trying to plot this signal, the plot will come something like this. Un plus 3 means it will be starting at minus 3, minus 2, minus 1 at 0 and then going forward, but subtracting it at un minus 3 means it will go only up to 2. From 3 onwards it is 0. And what is this signal? This signal is basically a gate signal, a rectangular or a pulse signal. Am I correct? So this is the Fourier transform of a pulse signal. Okay, this is the Fourier transform of a pulse signal. You will get something like this every time you do it for a case of a rectangular pulse. Another problem, it looks like a complex problem. You are having 0.5 raised to power n u of n and 2 raised to power n u of minus n minus 1, and here what we are having is a right sequence and a left sequence. Okay, if I am going to draw it for u of n positive side, it will be a decaying values. Okay, it will keep on decay. Similarly, in the negative axis also it will keep on going in the decaying values, because it's all going to be equal to it, because the value of this one is greater than 1. So that is also going to go down. So for such a sequence, what is going to be the Fourier transform? For finding that, we will use the linearity property. So first we will say, we know that a raised to power n u of n, the Fourier transform is 1 divided by 1 minus a e raised to power minus j omega. Okay, where did we get that? If you remember, we had solved and we had found out that the DTFT is basically given by this equation. Similarly, for the case of minus a raised to power n u of minus n minus 1, we had got the final answer to be again the same equation, if you remember. So using these two only we are going to solve. So, and we know that minus of a raised to power n u of minus n minus 1 gives the same value, that is 1 by 1 minus a e raised to power minus j omega. But since here it is going to be positive, what I will do is I will take this negative, multiply it with another negative, so it will become positive, but in the other side it will get minus. Therefore now, using the linearity property, which says that, you know, if you multiply and add, in the other side also it gets multiplied and add. So based on that, we can directly say that the Fourier transform of x of n, which is this particular equation, is, for the first one, using the formula, you know, we will write 1 divided by 1 minus, here a is 0.5, so 0.5 into e raised to power minus j omega, plus minus of 1 divided by 1 minus a, in the second portion it is 2, so 2 e raised to power minus j omega. Now we can do the cross multiplication and all, but that is not required generally. Okay, so now sometimes what will happen is, this question may come for, let's say, 7 marks. Then you have to do this, do or solve this. That means you have to show, solve. Okay, show solution. So solution of how you get this. Okay, that means instead of putting a, you put here 0.5, instead of a here you put as 2. So you can individually solve this and then using the linearity property show to be the answer, for the answer to be like this. Okay, we will do more problems in the next class. Thank you.